Hello. So last lecture, we saw the first representation learning uh, discussion. This is the second one, and there'll be a third one in the next week. In this, essentially, we are going to look at metric learning. Now, uh, what, what do we exactly mean by metric learning, and why is it a representation learning type? So in representation learning, we were trying to generate the data back or form a compression or some other representation, or even an embedding would satisfy. Now here what we are saying is they were task agnostic. So let's find a representation that is vectorial and is cognizant of a task. So here we don't actually care how accurately we represent the input, but especially in supervised metric learning, what we want to do is that if they belong to a particular class, the vectorial representation should be similar, and if they don't, then they should be dissimilar. Now, for example, when we discussed word embeddings, we did not have this idea that similar words should be together, except of course in the fact that if the words occurred in similar contexts, they should be together. But after training, we found that synonyms were closer together, they had similar relationships, and so on. So in that case, it was a happy journey where similarity in one space translated to similarity in other places. Here we make a distinction that the first methods we saw were just aware of the data. So we say similarity of the data alone, but here similarity is based on a task. So that is metric learning, where we want to keep the vectorial representations at a distance. So metric, of course, can also mean distance, at a distance that captures the task that we are trying to learn. So here, cannot is a strong word, but what I mean to say is if I have a classification problem, a two-class classification, then representations for one class objects will be quite similar. They'll be very close together, but their inputs can actually be very different. So this notion is what differentiates what we saw last class with what we'll be seeing in this one. So what we are trying to do is that distance between similar objects is minimal and distance between dissimilar objects is maximum. So what is a metric? Metric is a function quantifies a distance between every pair of elements in a set. So it's also a measure of similarity. So in this set of literature, you will find words distance and similarity used interchangeably. So higher the distance, lower the similarity. They have an inverse relationship. Lower the distance, higher the similarity. And they have these nice mathematical functions. The distance is always non-negative, and f of xy is 0 if x is equal to y, because we know that if two objects are exactly the same, then the distance between them have to be 0. Symmetry, f of xy if f of yx. And most importantly, this is what defines distance, which is the triangle inequality. That is, f of xz is always less than or equal to f of xy plus f of yz. So metrics have been studied by scientists theoretically and practically in many situations. And these kind of properties from linear algebra give us a nice sort of boundary to what we are trying to learn. Now, you might have seen these distances before, the Euclidean distance or the Manhattan distance. The Euclidean distance is what we call L2 and the Manhattan distance L1. The Euclidean distance between 2 points is square root of the sum of squares, and Manhattan distance is basically modulus of the sort of steps you need to take in the x and y direction. So the Euclidean distance is more complex, it's quadratic, and the Manhattan distance is in the linear, and so on. So these are just examples of metrics. Now, what we are going to do in this lecture is see how we can use deep learning networks to learn this metric and how we can make it aware of the task. This lecture is about supervised metric learning, and next week we will see unsupervised metric learning based methods. So, yes, as I was just mentioning the types of metric learning. In supervised, we know the task and similarities based on the class. In unsupervised, it's based on data. It's sort of like autoencoder, but there are notions of similarity and dissimilarity as well that we will explore in the next class. So, metric learning is not something new. It's not something that came for deep learning. There has been a lot of work right from the 80s in metric learning, and they're often classified on parameters like what is the paradigm? Is it fully supervised, weakly supervised, semi supervised? It can also be unsupervised, which we will see. Then whether the metric is in itself linear, non-linear, or local. Local in the sense, this is an interesting thing in vectorial representations, where you say that some properties are true only locally. For example, in KNN, in K nearest neighbors, you're taking basically the distance of only the nearest neighbor. So that is called a local kind of metric learning. Then you see whether it is scalable with respect to the number of example, with respect to the dimension. In deep learning, of course, for us, more the data, better it is. But you can imagine it takes more time to learn. And optimality of the solution, whether it is local or global. Then we see whether the metric performs a sort of dimensionality reduction or not. Now, this huge body of work was done using statistical methods initially before the deep learning methods started to dominate. Now, the reason this became important is that because we are dealing with vectors, defining how distance is defined in this vectorial space drastically changed how your performance is in these tasks. So, for example, in supervised learning, you learn with labeled data. Your approach is to collect a large data set, label the data, train a model, and then you learn feature representations. Now, unlabeled data is, of course, we've seen clustering, we saw autoencoder last time, and we'll be seeing more metric learning methods. So, of course, because I'm using autoencoder, you might ask what's the difference between representation learning and metric learning. The difference is quite small. It's just how we use it in the future. Now, self-supervised learning is, of course, with its own thing, which we saw last time. So, the wide spectrum of these metric learning methods will become clearer with the next week lecture. But bear with me, now we are looking only at supervised metric learning. So in the self-supervised task, what we did was, of course, we exploited some property and generated the output, which then we use for downstream processing or the transfer learning. Now, Shiva was talking about image augmentation. One of the famous image augmentation techniques is to just rotate the image. And we will be seeing what this pretext task is later on. So the idea is this. I have a pretext task where I sort of inculcate this notion of similarity and dissimilarity. In a sense, I know down the line it's going to be used for classification. And I want to say that some images are similar and some images are dissimilar. However, the catch is that I don't have the ideal amount of labels for all these classification tasks. There are some classes that have very few labels and there are some classes that have a lot of labels. When I have this kind of an representation, it is very hard to generalize. So what I do is that I use the supervised metric learning, but the set of data that I use for supervision is something I have constructed artificially. So what I'll do in the case of images is I'll take a set of images and I will create noisy images and I'll create rotated images. Now I know rotated images and noisy images uh, need to be close to the input. Then I take other images from the data set and I say these two should be far away from each other. The vectorial representations should be far away from each other. Now, this after I get this distance metric, I will push all these vectors to a different space, and this is what will be used for transfer learning. It will become clearer with some of the examples. And I want to quickly spend some time on the Mahalanobis distance because it's quite interesting, where it's a sort of unsupervised metric learning task, where what we want to see is that if points occur around a mean or a variance, then they're actually equidistant to each other. So you can imagine what Mahalanobis was trying to say is that all of these sort of belong to the same class. So if I have sets of data that sort of cluster together, then I want to say they're equidistant or close to each other. So this was done by introducing into our Euclidean distance formula the covariance and mean of the data. So Mahalanobis is a famous statistician. He was in our planning commission, an Indian scientist and statistician, and you can read up about him. It's very interesting. And without him, this entire section of algorithms would not have come into place. So I found that quite interesting. And this idea of changing the vector space for learning a metric is what we are going to see in this lecture. So we straight away go off into the deep learning models because that's what this course is about. But a more gentle introduction would have been to look at all the metric learning algorithms that are there and see what is the impact of CMAs network on this. So here is the idea. All these methods are actually very popular for images and videos because it's very easy to do the augmentation. You can rotate the images, you can change the color of the images, and so on. In text, it's much harder because we don't know how to augment text data. Having said that, I have used this quite a lot in my research in NLP, and towards the end of the course, I can give you an example of how I've used it. It's just that it's harder. You need to invest a lot more effort into generating these similar and dissimilar patterns. So here what we have is a pair of input images, and we want to know how similar they are. And the output, it can be either 0 or 1, or a real number, or the actual distance or metric, which shows how far away or how close they are. So why do we call them CMAs network? CMAs means someone or something from Thailand. But here, of course, that's not the reason. We take it from the word Siamese twins or conjoined twins because we are simultaneously going to learn metrics for things that are similar and metrics for things that are not similar. So this notion of Siamese twins is what gives the name CMAs network. So this is the architecture. So I have two inputs, x1 and x2, and the distance between them, the Euclidean distance between them, is what I'm generating. So this is sort of a dense layer, which is a representation, and okay, that is not actually depicted here. So basically, inside this, you have a network that will finally output a vector. Similarly, in this, there is a network that will finally output a vector. The distance between these two vectors is what is represented here, and this is your Euclidean distance. Now the catch is that the weights of both sets of data are tied. So we can only update this. So whenever we update something in this weight in backpropagation, we have to update this as well. Where have we seen this? So in RNNs, for example, the weights were tied for the hidden state. So it's the similar notion where you have to maintain the weights in both sides. Now, why are we doing this? We want to say that x1 and x2 are represented in the same way. It's just that the distance between them is different. In the sense, the weights are the same, and it's a function of whether it is x1 or x2. And we get the distance between them. Any questions till now?
No, ma'am.
Okay, thank you. So I'll continue. So what can we look at in terms of images? So if we have similar, so this data set basically takes the direction, and here we are taking basically the image and a slightly tilted darker image, and we want to say this is the difference between this is small, and we want to say the difference between this, which are in completely different directions, this is large. So how do we go about doing that? For that, our loss function right now is, again, you can imagine, though we are doing back propagation, the loss function at this moment is dependent on these distance values. And that is described here, where basically, if it is similar, we simply take the distance between them. But if they're not similar, we want to increase the distance between them. So I want to say that if they're not similar, so usually we take the margin as 1 or something. So we want to say that it's either going to be 0 or 1 or 1 minus that distance. So here we are going to maximize, and here we are going to minimize. You'll remember that loss we always try to minimize. So we put negative of that so that this distance becomes maximized. So that's why I did RBM the last lecture, because this is also an idea of contrast. So we had this positive and negative influence notion, and we do the same thing here, where if it is similar or a positive influence, we do it in one direction, and if it is dissimilar, we do it in another direction. So what is the flow of the network? So we take pairs of the input, we tie weights together for both sides, and this is the representation learning part. And the distance between the intermediate representations is dependent whether the pairs of input belong to the same class or different class. Here, same class and different class in practice is an augmentation we have done and not the original classification data. Then we use this loss to do back propagation, taking care to update weights simultaneously. It's all. So again, the math is going to be a bit complicated because you can only take partial derivatives and not full derivatives and so on. So drawback, of course, is that as with many other representation learning techniques, it's very dependent on the data, and the distances are pushed together or further without notion of the data itself. I mean, there is some notion, but not much. And it's dependent on the task, cannot be adapted to other tasks well. Here, task, of course, I don't mean the final task, but how you do the augmentation. That's what I meant. Now, CMAs Network, as with all things in deep learning, have so many flavors. I remember somebody asked me a question on convolution, whether the strided convolution occurs horizontally, vertically. The thing is, there is no set. It's not like an algorithms course where you have a set idea, a set proof, and how we are going. It's basically a set of experiments where we have a core idea that we are building upon. So in CMAs network, you can either take your two inputs and just pass it on to the shared weights, or first you can have a branch network that learns something, and then the weights are shared, and then you pass it on. So yeah, we can do all kinds of architecture, but the idea of the CMEs network is that we have two inputs and we're trying, which are actually twins of some sort, and we're trying to understand whether they're closer together or further apart. Now, why are we doing all this? If we can just classify, if we can just anyway we have labeled data, especially in the context of supervised metric learning. So that's because when we use discriminative methods such as neural networks or support vector machines, we need to first know all the categories, and we need training examples for all the categories. Now, this is not a problem largely in text where because we have good annotated categories, but there are many problems. For example, if your task was to classify documents into categories in Wikipedia, then we have a lot of categories and we have few examples only for those categories. So in these kind of situations, we want to bring about some kind of representation and then push it further on in transfer learning. So this is the extremely popular paper for similarity learning, which is the CMAs networks. And what they did, this came out in 2005. So here the idea was to use a similarity metric to identify faces. So face recognition research was at its was just starting in computer vision, and the idea was that we learn similarity metric from the data, and it can be used for recognition of verification whether categories is very large or not. Here category is very large because in essence we are going to say this person is verified to be this name. So the name itself could be a category. It's sort of like sequence. So this idea of representation learning came there. So they successfully showed that they can recognize faces that were not there in the data set. In the sense, later, if some other person registered their face photo, then they were able to correctly identify later on. And it comes in speech also. We have speech verification techniques and so on. So in all of them, this is quite useful. Now we come to something known as Triplet Network. It combines the idea of both CMAs network and autoencoders. Once again, we are not generating the input again, but we're just looking at the idea of using the input in itself. So for example, if we have a negative example and a positive example, in a sense, the distance between this and this augmentation is dissimilar and the distance between this and this is similar. Then we have two sets of distances where we want to keep this low and this high. Also, we have another distance on top of this which compares these two distances. And again, you want to put them as far apart as possible. In a CMAs network, what we would have had is simply the distance between this and this. We have known either we would have had it between these two or between these two or these two. So this kind of notion brings about more complexity, and also it simultaneously learns both the similar and the dissimilar representations. So what it does is it brings about a kind of ranking in your data where you not only see whether they are similar, dissimilar, closer, further, but also how the distances relate among themselves. Okay, these two are similar, but how similar are they? These two are dissimilar. How dissimilar are they? Okay, this is similar, this is dissimilar. What is the degree of similarity and dissimilarity between them? So this is a stronger sort of network. But always remember, whenever we go for a more complex model, we will have to compromise somewhere on, say, the training time or the quality of the training data and so on. But this is a little bit more robust than CMAs networks, and that is why we go for it. So what are the applications of CMAs networks? So the first, which I've been talking quite a lot about, is transfer learning, where we learn this intermediate representation in using this augmentation, and then we have a new domain whose input we take and then build a classification model. This we saw even in the downstream processing in our autoencoders and so on. The next one is manifold learning. Manifold basically means a representation of high dimensional data. So this is basically a visualization technique of which the TSNE is very popular now. They're basically dimensionality reduction techniques, which we saw in PCA or autoencoder and so on, and also in CMAs network, because generally the intermediate representation is of a lower dimension than your input. And then we can use it to produce clustering, because once we have representations, we can learn more about the data by clustering. And let's have a quick look at some of the case studies. So this is an interesting context encoder. So what we do is, in this data augmentation technique, we just remove portions of the image and expect it to generate a part of it. Of course, this example would have made more sense in the autoencoder lecture. Yeah, apologies for that. But basically to say that the distance between this image and the new image is less. So what happens in CNNs and things like that is that we concentrate on portions of the image independent of the context. So in this, we are forcing the network to learn the context and reconstruct it. The next case study is empath. It's an emotion model where it's also a text kind of model and image. Sorry, this is an image emotion model where we're trying to get the emotion based on the facial expression. And the interesting thing is, using the CMAs network and image augmentation, they were able to get wonderfully separated representations based on every emotion. So this is how it looked in the reduced dimensionality space, that very neatly all the emotions sort of clustered together in the CME space. So that is the summary I have, that we are trying to learn a distance or a similarity metric, and this generalizes to unseen data. It's useful for downstream processing tasks, and we can do dimensionality reduction or transfer learning. In the next lecture, we'll see unsupervised metric learning, and thank you.